Okay, so is it visible to all?
Yeah, it is visible.
Is it?
Yes, it's visible.
Okay, sorry. So today we'll be discussing complexity analysis. So mainly we would be discussing complexity about space and time, because these are two most important.
Sure, recording will be provided na, after the class.
Sorry.
Is this class being recorded?
Yeah. Okay. So today we are going to discuss complexity analysis. This is one of the most important things in algorithm design. Like, wait. Okay. So this is one of the most important things while we write code and design new algorithms. So, and often in interviews too, you would be asked questions related to complexity of the code you have written. So, this is that's why it is so important. So basically, like I and Kiranmoy would be taking this session together. I would be mainly discussing the theoretical parts, and Kiranmoy would will go through some examples, and sorry, Kiranmoy would go through some examples and tell you how some algorithms are better than others in terms of complexity and like time complexity and space complexity. Like, okay, we'll get to know what these are. So let's start. So I have divided it into 6 parts. First, we'll go through what exactly is an algorithm. Then we have what do we mean by computational complexity, right? Then we would be discussing why there is a need of analyzing complexity of every algorithm that we write. Then we'll come into actual analysis of the algorithms. There are basically 3 cases. Sorry, best case, average case, and worst case complexity. And then we would come to asymptotic analysis. There are 2 kinds of analysis, amortized and asymptotic. So whenever we will be talking about complexity, we will be mainly talking about asymptotic. We can ignore amortized analysis for now. And okay, then Kiranmoy will go through some examples and show you how to find complexity of any algorithm, and how to like reduce the time complexity of any code that you write. So let us get into it. So what exactly is an algorithm? So like we can define an algorithm as a set of instruction or basically a procedure to solve a given task or solve a given problem, right? Like if we have a problem in hand, there are some steps that we need. Like, for example, we are given some problem to solve. So we have to take care of some steps to achieve at a particular solution, right? So so it's the same here, like we feed those steps to the computer to solve an algorithm, and the computer performs those steps, and it returns us the solution, right? So an algorithm is the idea, yeah. So it is basically like everything, every code that we write is basically a piece of algorithm, right? Uh, we we have a problem, and if we are trying to solve it, like we have to give some set of instruction to the computer, the approach. The computer cannot figure out on its own how to solve the problem. That's where we come into role. So there we feed those set of instructions to the computer, and then it solves the task, right? Solve the problem. Let's take an example. We have a list of integers, right? Integers, in last session, you must have come through integers. So for example, we have a list of integers, right? And our task is to sort a list of given integers, right? So the user provides the list, I mean all the integers. So the input is for example, A1, A2, A3, and each AI represents a particular number, right? So this is not in sorted order. It might be in sorted order, but still, like, we need to sort it, right? So this is the input, and then we know that what output we are expecting. Output should be a permutation of this list, right? It would be permutation of this list such that every next integer is greater than or equal to the previous integer. That's what sorting is. So to achieve this output, we need to perform a set of instruction, right? One of those instruction can be like, we can generate all the permutations. Like if we have n numbers, just generate all the permutation, and for each permutation, just keep checking if the list is sorted or not, right? That can be an approach, but that approach would be the worst approach to take. Like if we have 4 to 5 numbers, then number of permutations would be like 5 factorial. 5 factorial would be like 120. So even for 5 integers, there are kind of like 120 possible permutation, right? And checking all the permutation is not possible. I mean, it's possible by human, but like, it's possible by computers, but like for us, generating all the permutation is not possible. But for even for computers, like computer might be able to sort the integers using this permutation technique for a small number of n. Like if n is 100 or 1000, like 100 or 1000 factorial can be a very large number, right? So so we know, like here we can say that that approach is not good. Why is it not good? Because look at the resources that it is gonna take. Like it will take a lot of time. Even if it is computer, it will take a lot of time to generate all the permutations, right? So okay, so it is what an algorithm is. Let's come to the next thing. Okay, computational complexity. So each instruction takes some resources. each instruction takes some resource to be performed. Like if we are performing any instruction, it is gonna take some processor power, or like it is gonna take some space in the RAM. Like we need some memory to store each instruction and each data, right? So performing each instruction is has some cost. Like nothing comes for free. So here also it has some cost. It will take some time. It will take some space. Okay. So here resources are, resources here, time and space. So these two are basically our resources, because if we look at a computer, right? Now computer has a RAM where it stores every data while it is computing something. Now in the RAM we have limited amount of RAM, right? Now RAM is very costly, right? RAM is not so cheap that anyone can buy, like, sorry. So what I'm trying to say is RAM is not that cheap. RAM is costly. So we have to optimize our algorithm in such a way that it requires least amount of space. Now, another resource is time. Like we as a user, time is important to us. Like if we are building some application for some user, and if that application is too slow, the user experience won't be good, right? We need our algorithm to solve a task as soon as possible. So, yeah, by resources we mean time and space. Okay, so computational complexity is nothing but like the amount of resource that a particular algorithm is going to perform. Okay. So next we have the need for complexity analysis. So yeah, like I told, resource is valuable, time is valuable, and space is valuable. Like RAM costs are very high, right? And the time of user is also very valuable, right? So, and complexity analysis is gonna help. See, just analyzing complexity isn't gonna do anything, right? Why we analyze complexity? Because to compare algorithms so that we can save some space, save some time. So just analyzing those things won't do anything. But like first we analyze an algorithm. If it is too slow, we come up with a better approach, right? If it is taking a lot of memory, we come up with a better approach. So that's why analysis is important. To like it indirectly helps in saving the resources, saving the space, saving the time, right? And to measure efficiency of two algorithms, like it can be a parameter, like analyzing the complexity or analyzing how much time it is taking, how much space a particular algorithm is taking. It is important, like to compare two different algorithms or like two different approaches. Like I just told you about permutation sort. So like what we are going to do is taking all the permutation of the integer and then like checking each permutation whether it is sorted or not. So now one might come up with something better, right? Something better. There are some other approaches for sorting, and to compare those, we have to look at their complexity, time complexity, and space complexity, right? And one of the most important thing is space-time trade-off. Generally, what happens is we can have a trade-off between space and time. What I mean by this is, like, we can save some time by allowing some more space, or we can save some space by allowing some more time. Uh, let's take an example. Like, for example, we have a supercomputer, right? It has very large RAM, so we can say that we don't have uh, any shortage of space there. So in that case, what we are going to do is we we will create a trade-off so that uh, our algorithm takes less time, but it takes greater space, because space is available to us. So, like, we can create a trade-off. But for example, we have something very small, like uh, like we can take any small device, IoT devices, and there we have very limited space. Like, even in our phones or even in our laptops, we have limited space, right? So there we have to somehow, like, create a trade-off between space and time. Sometimes it will take more time to perform that, to solve that problem. Sorry. Okay, so now we have best case. Let me check if someone is trying to join. Okay. Okay. Till now, anyone has any question? Like, things that I explained?
Simon,
You can, yeah.
can you briefly explain the space-time trade-off? What actually your problem?
Yeah. So let's take an example. Like, let's say mm, okay, we have an can we like, I need to show some code for this space-time trade-off. Like, I'll show an example in the last, right, about this.
So it
How
is basically like the trade of space and time. Like, if a certain algorithm is taking more space, then it can do the job in less time. Suppose our hardware have more space, so but our hardware is not capable of doing fast computation. So in that case, we will use that algorithm which use more space, but the time complexity is less. But in case of certain other algorithm which may take some less space, but the time complexity is more. So in case of very small chips like Raspberry Pi or any other small computers where the space is not that much available, the RAM is very much low in size. So in that case, we will use some sort of algorithm which may take more time but uses less space. So these things will be more clear when we will be like studying different type of algorithms. So because the complexity analysis is a trait of an algorithm, so without showing algorithm, it is very tough to show the trait.
Yeah, exactly. And for this, like, I'll show an example with two different codes. One code, like, both will be solving the same question, same problem, but like one will be taking more space but less time, and other will be taking greater time but lesser space. Okay, so by this I mean like if we have a supercomputer, like we can have terabytes of RAM there, right? We don't have any shortage of space there. So what we can do is we can come up with an approach, like even if it requires more space, we are fine with it. Okay, what we want is we just need uh, the solution to be the solution to take less time, right? And let's take some small microprocessor or something like uh, any device, some small device like our mobile phone or anything. It can be yeah, like Raspberry Pi or Arduino are great examples. There we have a limited space, very limited space, right? So to solve a task, we we have limited space, but like we have no option. Like so there, what we will do, like yeah, we'll be okay with whatever time it is taking, because we don't have any option. We have limited space. So like uh, with different approaches, different algorithms, we can like create a trade-off between space and time. That's what I mean here. And yeah, at the end, I'll be discussing an example where we'll be seeing how this can be achieved for a particular problem. Any more question?
No, Simant.
Okay, actually, I had thought of this space-time explaining this in the bonus section in the last. If time permits, we'll have a bonus section after this is over. Okay, so let's go to yeah. So now we have analysis, best analysis of our approach, but and like we can suppose we have an algorithm, we have a set of instruction, right? So the best case, let's go to worst case first. The worst case is, and we have a problem at hand, right? The worst case will be when the algorithm will be requiring maximum number of steps to solve that problem, right? That would be worst scenario, right? The best case would be like when our algorithm will run for like minimum number of time to solve the problem, and the average case will lie in between. Like so, let's take an example here. We have a list of integers, right? This is a list of integers, right? We have 34, 2, 150, 2, 20, 23, 200, 20, 50, and 100, right? Now, problem is to check if a particular element is present in this list or not, right? So let's how are we going to check? Well, like, well, how are we going to check if a particular element is present or not? Suppose that element is x. Now we'll compare with x with our first element. If it is equal, then well and good, we are done there. If it is not, we'll go to next element, we'll check. If it is not, if it is equal, then yeah, we will declare that yeah, it is present, and we'll like end the program there only. Like yeah, we have found, so we'll end the program there only, where we have found it, right? So here we have a list of integers. Now we have to check if sorry, 100 is present or not, right? So let's see what we are going to do here. Okay. So we are will first compare 100 with 34, right? Let me check how many elements are there. 3, 3, 6, 3, 9 to 11. Okay, okay. So we have 11 elements. So we'll first compare 100 with 34. It's not there. Okay. We'll go to 2. We'll compare. Yeah, it's again not there. Okay, sorry. I have taken 100 2 times here. Let's make it 105. Okay. So we'll check with 2. Compare with 2. It's not there. Okay. We'll then go to next element. Compare with 1. Not. It's not there. Now we can see that we will have to perform 11 comparisons to declare whether 100 is present or not, right? With each number we are comparing, right? So this is a case of this is kind of a worst case, because we are performing we are going through each element, and we are comparing with it, and 100 is present at the last, so we are taking maximum number of steps, right? So this case is worst case, right? Now let's take 34. We compare with first element. Yeah, it is equal. So we declare in the first step, yeah, 34 is present. So here we are taking a minimum number of step, right? We just took one step and we declared, yeah, 34 is present. So this is a case of best case scenario. Now let's come to 23. Now 23 is present in between. Let me take 1, 2, 3, 4, 5, 6. Okay, it's exactly in between the extremes. Okay, so it is not going to take neither maximum number of steps nor minimum number of steps. So this case falls in average case, right? So here we can see like how to compare algorithms case by case, right? But this is not a robust approach. Like this approach depends on input, right? Input of the user. So for a particular list of integer, we can say that this is, and a particular integer, we can say that this is worst case, this is best case, and this is average case, right? So now we don't know, like there will be cases when we won't be knowing that we won't be knowing the list of integers and or the integer. So in that case, first like this kind of becomes a probabilistic approach, predicting which is worst case, which is best case, which is average case, right? Because we have the test case, so we are able to tell which case is worst, which case is best, right? But this is not an robust approach to analyze an algorithm. So here is a diagram, like for a particular value of n, let's say n is 4, okay, there can be multiple instances, right? Each dot here represents an instance. What I mean by instance is, let's say we have 4. So like let's say n equals 11 means there are 11 elements present in this list, right? And this instance, like this list, this particular permutation, and the given test case, that is we have to find 100 is present or not, is a particular dot. If we for n equals 11, this represents a particular dot. Now each dot is an instance. There can be many instances. Okay, so so here our analysis is kind of like this. For n equals 11, here only till 4 is given, but like there can be 11 can lie somewhere here, and like for that we'll have some best case, we'll have some worst case, right? And we'll have some average case scenario. But this particular approach is dependent on the what can I say, like particular n. For a particular value of n, size of input, we can take this approach and analyze it. So this is not the best approach to take while analyzing algorithms. So we have something better. Now this is called asymptotic analysis. Here, asymptotic function is nothing but like it measures the order of growth of the function. Like our algorithm is function. Okay. Now here I have written that the best case, worst case, and average case time complexities for any given algorithm are numerical functions over the size of possible problem instance, right? If I talk about it, this is one of the problem. Like this is not a general solution to compare the to like analyze a particular algorithm. We'll come to something more general. This approach, asymptotic analysis, is more general approach to analyze a particular algorithm, right? So it is nothing but like it measures the order of growth, right, as the size of the input. Order of growth as the size of the input tends to infinity. You can say n tends to very large. Size of the input is n, and n tends to very large, tends to be very large or very large number. So this analysis is helpful when we are talking about n with something greater than n naught. N should be greater than n naught. Like okay. Sorry. Okay, so let's see this diagram. So here we have this function fn. This is our approach. This is our algorithm that we have written. Okay, in terms of n. N is the size of the input. N can be anything. I mean, it depends on the size. Like here we have size as 11. So we have, for worst case, we had to compare 11 integers, right? But here, okay. So in asymptotic notations, we have three types of notations: big O, omega, and theta. So big O denotes the upper bound of a function. Okay, it means that for a large value of n, and n is greater than n naught, for n greater than n naught and n is very large, our function can never be greater than big O of n. I mean, what I mean by this is like this is kind of an upper bound for this function. Okay, so the worst worst that can happen is it can be equal to this, but it can never be greater than this. And we have other notation that is omega of n, that is used to omega of n denotes the lower bound of the function. Like for n greater than n naught, our function fn can never be less than our lower bound. And we have theta of n. So like if we have upper bound and lower bound, so this means that our function can be considered as bounded between two limits, and we will have a theta of n. Basically, these approaches are more useful in theoretical science. So we'll just go with big O of n because it is most useful. Big O of n now big O of n is the upper bound of any function or any set of instruction that we have written. It is the upper bound. Like it cannot surpass that. Okay, so yeah, so the running time can grow at most as this much. As an example, I can say that, for example, like I have 10 rupees, right? And I go to a friend and I tell him that I have at most 20 rupees, right? So I am not lying to him, right? I told him I have some amount of money and the amount of money is at most 20 rupees, right? So here I am not lying to him. I am telling my upper bound, right? Here also it's just an assumption. How worse can our algorithm go? It is our assumption. So the maximum limit will be O of n. O of g of n, whatever function we have. Right. Now, analysis can be of, when we talk about analysis, it means either, as I told, space analysis or time analysis. So time analysis is nothing but a function describing the amount of time an algorithm takes in terms of the size of the input to the algorithm. Yeah. And space complexity is it is a function describing the amount of space an algorithm takes in terms of the amount of the input to the algorithm. Okay. So we have covered this. Now let's see this. This will make things more clear. Like for example, we have our function as this. Now our function denotes the number of operations or the number of instruction that we are going to perform. Let's say we have n as 40. Then this function will tell us that 10n cube plus 24n square plus 3n log n plus 144 is the number of operation that we are going to perform. Okay. Now, n here is the size of our input. Okay. Now this function fn will be less than equal to this, right? Will be always less than equal to this. Okay. This function will be always less than equal to 10n cube plus 24n cube plus 3n square 3 n cube plus 144 n cube, right? And this will be equal to this should be equal to this, right? And we are replacing this sum with a constant term, something c, and we have n cube here. Okay, so this will be equal to this, and the upper bound of so here we can replace c by big O of n. That's what we do in when we talk about analysis in terms of big O of n. That's what we do. We replaced the upper bound, the constant of the upper bound, with big O of big O. Right. This big O denotes the upper bound. So if anyone has any question, you may ask now. So I told that now this there is sometimes a confusion that best case is worst case is denoted by big O of n, average case is denoted by we call it omega of n, and worst case is denoted worst case is denoted by omega, and average case is denoted by theta of n. But like I too had confusion before I read about this, but it is not true. Right, this analysis is completely different from this analysis. Here we are talking about the size of the input, size of the array. Like here we had the worst number of that we performed was 11. That is size. That is equal to size of the array. Now, if size n, we are going to perform at max n number of operation. Now, in asymptotic analysis, what we do is we just create an upper bound for our function. Our function represents nothing but number of instructions that we are going to execute. Fn is nothing but number of instructions that we are going to execute. And we are here setting an upper bound that, okay, our function can never be greater than this, right? So the maximum number of operations that we can perform is big O of function n, which is here O of for this. If Fn is this, 10n cube plus 24n square plus this, then the maximum number of operation that we can perform is C some constant into n cube, and that constant is given by this 10 plus. That constant is basically not important. What is important is the order of the term that is after the constant, that is n cube. N cube is important. So, anyone has a question? Okay. Now, some common order of growth that we generally see in analysis is, now we know O of 1. O of 1 means that constant time, means only one instruction. I mean order of one instruction, not exactly one instruction, but like it can be 5. O of 5 is also equal to O of 1. right? Because if we see about see order, like let me share. Okay. Now let's okay. Let's see we have let's say we have O of 15. Right. Now we can write O of 15 as O of is it visible, the Jamboard?
Yeah, it is.
Anyone please unmute and
Yes.
okay. So for O of 15, right, we can write it is nothing but 15 into 1, right? 15 here is constant, okay? So we can just treat it as O of 1, right? Now, if we have something constant into n, right, we can just say now n here is very large. N here is very large as compared to this constant. Okay, so for this, we can write this assumption would be equal to this. Okay. Now, for example, we have something like O of m plus n. Right. Like it should be clear. Like it's just an assumption that we are doing, right? We are not bothered about exact number of instruction. We are just about the approximate order. Okay. Why we are bothered? Why we are just bothered about that? Because let's say we have our function as something constant c1 n square plus c2 n plus c3, right? And c1 is much less than n, c2 is much less than n, and c3 is much less than n. Okay. Now, if our n is very small, right, then we will have some let's say this is equal to k for very small n. Now, if n becomes very large, right? If n becomes very large, we can see that c1 n square, like for example, n is 10, right? N is 10. We can say that, and let's say we have c3. Let's give them some value. Like our function is n square plus 6n plus 7, right? Now, if n is 10, this would be equal to 100 into 5, that is 500 plus 60, 560 plus 6 plus 7, right? 567. Okay. So what we did was this was 500 plus this was 60, right? Now, if n is n is very large, like 10 to the power 6, right? Now here we can see that this term would be 5 into 10 to the power 12, right? Plus 6 into 10 to the power 6 plus 7. Now these two terms are insignificant when compared to this, right? Remember, when we started asymptotic analysis, we told that we analyze for n when n tends to be very large number. It is very large number. So this term is very insignificant in regard to this. So we can say that approximately this function is performing n square instructions. For if n is very large, then this function is kind of telling us that we are going to perform approximately some constant into n square instructions. So we write it as big O of n square. Right. So if we have some constant here, constant term, it does not depend on the size of the input, it is constant. So like that would be approximately equal to O of 1. Okay. So that's what I meant by this. So now some common orders that we see are O of 1, that is constant time or constant space. Here I am talking more in terms of time, because you will like get to see know more about space after you learn some data structure, like how much a particular array or a particular data structure is taking space, right? So both are kind of similar. So you can relate whatever I'm explaining here there also, right? So O of 1 denotes constant time or constant space. O of log n denotes logarithmic time or logarithmic space. Similarly, O of n is linear. O of n log n is called n log n. O of n square is quadratic. O of n cube is cubic. Then we have here O of 1 represents something constant. So n to the power, it can be 1, 2, 3, 4, 5, 6, anything. So that is basically, in general, that is called polynomial. And we have 2 to the power something O of n. So that is exponential. Now, if we compare, now O of 1 will take least time, and O of log n, and O of log n will take lesser time, sorry, then O of n, and O of n log n will take lesser time than O of n square, and yeah. Okay. Now let's see some cost of some common operations. Yeah. So like each time we create or assign a variable, this takes a constant time, O of 1. Okay, because we are just writing one instruction to create a variable, right? So it will just take one unit of time. Okay, so that takes constant time. For performing any arithmetic operation, like we say int a equals 5 plus 15. So that is gonna take a constant amount of time because it is not depending upon the size of the input, right? So or any conditional statement like if else, these all will take, each line will take a constant amount of time to execute. Now let's say we have to iterate n times, right? N is provided by user. Okay, it is size of the input or anything it can be. Let's say we have an array of length n. So here, and that n can be array size of that array. Now if we are iterating n times over a set of instruction, each having a cost of on. For example, let's say the instructions that we have written here. Now these take O of 1 time, right? If these take O of 1 time and we are performing it n times, then obviously that the cost would be O of n, because we are iterating n times, right? Now let's see, we have this code. Now the innermost loop will be executed n times. This is a nested loop. Okay. Now this innermost loop will be executed m times, right? And for each iteration of the outermost loop, we are iterating innermost m times. So like we can say that the cost of this as a whole will be O of n into m, because like we can say m plus m plus m plus m plus m n times, right? So here we can write cost as big O of n into m. Okay. Now we have like let's see, here we are performing some iterating n times, and outside of this loop again we are iterating m times. So like we can say that first we are going n times plus n times. So the complexity would be O of n plus m. Now if m is very large than n, right, then O of m plus n can be approximated as O of m. Okay. So I hope this is clear. Now let's say we have some instruction that takes O of log m times, and we are repeating it n times, right? So that is gonna take n into log of m. Okay, these are some simple examples. I have a quiz. Now you have to like answer like how many times this the cost of this operation. Like what we are doing is we are initializing with 0, and we are going till n, and each time we are multiplying I and assigning, each time we are multiplying I with 2 and assigning it to I again. Okay. So if anyone can solve it, we just want to know, and we have set of instruction that will that with constant time complexity. Matlab, I mean whatever we have here takes O of 1 time. Okay. So what will be the complexity of
Smith, I guess it will be better if it's answered after the examples. I think you will be able to answer it.
All right. Actually, my part is over.
Okay.
I had kept this indent, and I have some references where you can refer to. Okay. Let me explain
Chat
this.
box में डाल दो ये सब reference.
It will be given in the group.
I'll share this slide. Okay. So. Should I explain it now? Like.
Explain it after the examples. I guess they will be more like get accurate after seeing the examples.
All right. So
Satvik, it is a good case, but it's not the correct. Okay, so it will like elaborate after the examples. So
yeah. So
until
Kiranmoy, you can present now. Like he'll explain the
okay
all the questions and examples.
Okay. So let me just share my screen.
মাইকটা ঝিরঝির করছে কিরণময়।
Is it not properly audible? Is it audible now? Hello.
একটু মাইক্রোফোনটা চেঞ্জ করে ইয়ে করতে।
Okay, just a minute. Is it audible now properly? Am I audible? Hello.
Yes, sir.
Okay.
হ্যাঁ চলে চলে
So,
বেশি
okay, let us just revise what Sumit taught just in a brief to get the to like before proceeding to the example, just a quick revise. So, Sumit taught there are like the asymptotic, there are asymptotic analysis of algorithm. There are many asymptotic analysis. Among them, the big O sign is very popular and widely used. There are other signs like omega, and but those are very rarely used. So majorly today we'll be seeing the big O notation. So what was the definition of big O notation? Let us just once see. So I hope my screen is visible. So the big O notation. So first of all, just a quick revise. Why do we need this like uh, algorithm analysis? Because to solve a problem, we need algorithms, and in order to solve the problems, we need to. There are not only one solution; there are multiple solutions, right? And this analysis gives us the analysis that which algorithm among them is the best to solve the problem on certain hardware, as Simit mentioned back then. So we need to compare the algorithms, which is more fast, which is taking less space or more space. That's all. So in order to compare the algorithms, we need this different kind of notation, because we can't just say that this algorithm will take this much time, because it will depend on the sample space that we are giving to the algorithm and the hardware it is being performed on. So saying time is not a very good way. So we need a good way. So the asymptotic notation is a good way to compare the algorithms. So what is the definition of big O notation? F of n is order of g of n if there exists a constant c and n naught, that f of n less than c into g of n for n greater than n naught. I know this definition might seem not that much intuitive, but you will understand it eventually. So what we are trying to define is to get a function g of n which multiplied by constant will always be the outer boundary of the function f of n. So after a certain n naught. So in case of any value after n naught will not have more value than c into g of n. Like any value of f of n will not have more value than c into g of n after this value n naught. So we can say that g of n is in like f of n is order of g of n. So okay, so let us just straight go to the examples. So first example, after so many theories, we will try to like this algorithm analysis or this asymptotic notation. These are the characteristics of an algorithm. So without talking of algorithm, we cannot totally understand. And algorithm will be taught in details in further sessions. This session is not for algorithm, but we need certain algorithm to see how it's working. So let's just start from basics. So let us find sum of first in natural numbers. So how a human would do? Okay, so before proceeding, if anyone have any doubt, please feel free to ask. Even use the chat box. Yeah, it is correct. It is login best too. So Sumit will explain it in the later part. So if anyone have any doubt, please feel free to anytime write in the chat box or come on your way. So let us find the sum of first n natural numbers. So suppose a approach of solving it, what can it be? Suppose a class 8 boy who have not yet been taught the arithmetic progression. How will he solve it? Suppose I am giving the boy number 5, and I am telling him that add all the natural numbers till 5 and give me the answer. So what will would that boy do? He would simply take 5 plus 4 plus 3 plus 2 plus 1, and he will stop here because 1 is the least natural number. So then he will add these numbers, and what will be the output? 5 plus 4 9 plus 3 12 plus 2 14 and 1 15. So he will just come up and say, okay, the answer is 14. So our first approach for this problem, which is to find the sum of first n natural numbers, will be the same approach of that class 8 boy. How is doing that? The naive approach, which is how we are doing it. Okay, let's first code this this thing which we said, the boy will just do this thing. Let's just code this thing in our IDE, which will give her more exposure to the coding, which we learned in the last day session. Also, after coding it, we will analyze how the algorithm is performing. So let me make what should be the program name? Okay, sum.cpp. As Fahim mentioned last day, we just include the header file. Formalities before any program. Then the main function. So what we'll be needing? First of all, we'll be needing an n, up to which number we want to find the summation till. So I will define int n. So this is an integer, and now what I'm gonna do is I'm just gonna take the input. So we may declare another variable which is sum, which is initially equals to 0, and what we'll do is sum equals to sum plus n. I'll explain why I'm doing this, and then what we'll do is n minus 1. Let us see if the code works. Okay. Okay, I just forgot. Okay, so the code is perfectly working. How is it working? It is using the same approach till this of this 8-year-old 8+8 guy. So what is he is doing that he is taking an n and he is declaring two variables n and sum. He is taking the input n, and until n is becoming 0, he is adding n to sum and reducing the value of n by 1. This line implies that the value of n is reduced by 1. This is a function, it returns the value of n. So you will like on practicing of C++, you will get to see this, get to like practice these things. So I hope after the last day session you practice and you know this much things. So what it is doing, that it is adding the n to sum and it is reducing n by 1. So when I am giving 5 to this loop, so sum is initially 0. So it is adding 5, then the value of n is becoming 4, then it is adding 4, then it is adding 3, then it is adding 2 until 1. And then when it's becoming 0, it's no more adding the thing and it is just giving the output. So let us analyze. Okay, so anyone have any problem in this code? Okay, so I guess not. If any problem, just write in the chat box. So let us see what is the complexity of this code. How many operations we are performing. So as taught in the theory part, we while analyzing the algorithms, we cannot talk of time, right? A certain algorithm, if this thing will totally depend on the value of n. If the n is very much big, it will take more time, and it will also depend whether I am running on your i5 computer or on my dual core computer. So it is totally dependent on that. We cannot use time. So what we generally do is that we define the function, like define the number of operations in terms of function, and then we use that function to get the order of the algorithm. So let us first find how many operations will this program perform. So this line is one operation and this line is one operation, right? Total 2 operations. So this 2 operation will run how many times? This loop will run n times, right? So the total number of operation of this much code is 2n operations. So can anyone tell me that what is the big O value for 2n operations, or what is the big O value of 2n, like as Simit, anyone in the chat box, like as Simit told, like just to ignore, suppose we have n square, so we n square plus 3n, so we ignore the 3n and we just take n square, so we have definite rules. What are those rules? So let me just revise the rules. Okay, so drop the lower order terms and constant factors. So when we have an equation function and we want to like get the order of it, so what we generally do, the rules are at first drop the constant factors and the lower order terms. Then we generally specify the tightest bound possible, and then we use the simplest expression of the class. So let us first drop the lower order terms and the constant factors. What are the lower order terms? There are no lower order terms. There is only one term, that is 2n. But there is a constant, right? We may drop the constant. So what left for us is the only n. There is nothing more. Yes?
Yes, n.
Okay. So we can say that this program will run on order of n. Right? Was it understandable why it is being order of n? Because the total number of operation is 2n, not 2n. I'm just like in the order of 2n. I'm being approximate because this is an also operation. Defining is also operation taking input. We can just ignore that this is small terms. We are talking of like the big time. The maximum time will be taken by this loop, right? When n is very big, like n is 1 crore, 2 crore. So there will be 2 into 2, 4 crore operations. So so 4 crore and 1 and 4 crore and 3 and 4 crore, just only 4 crore. Those are similar. So we can just ignore those. So total number of operation is 2n because there are 2 operations in this loop and the loop is running n times. So we can say this is the order of n. Was it understandable? Was this approach and this the big O notation, why it becoming order of n, was it understandable? Please say. Okay. So if you have any doubt, you can just say in the chat box. Okay, so now we are moving from, we are seeing that what the class 8 guy would do, right? It is the approach of class 8 guy, which is just adding 5 plus 4 plus 3 plus 2 plus 1, who have not yet learned what is arithmetic progression, right? I have already given a hint to make this algorithm more efficient. So what we are trying to do, we are trying to find, like, let me just write the problem statement. We're trying to find summation of all natural numbers till n, right? So our algorithm is taking order of n times. So can anyone suggest me anything better which we can do in order such that we don't have to, the time complexity gets reduced from this order of n, so that it becomes in much low operations. We don't have to do this 2n operation. Can anyone suggest me anything? I already have given the hint. It is arithmetic progression. So can anyone come with a better approach so that we can reduce the time complexity from order of n to anything which you can suggest? Can anyone?
What?
Like this was understandable, right? Because like the why it is being order of n, right, Deepak?
Yes.
Okay, so can you suggest me another algorithm, or like the boy is, what the class 8 boy is doing, he is just adding numbers. Can you suggest me another algorithm or another steps to find the summation of all natural numbers till n without needing to do 2n operation, so that we can reduce this?
वही arithmetic progression वाला formula use कर देंगे.
Exactly, we will just use math. Just a minute, I'll just make that minute. So what we'll do that, now we are reading in class 11 or 12, so now we know the formula of arithmetic progression. While it may seem simple that, okay, why we are even doing this in the first place, this is very much efficient. So what?
उसका order 1 constant हो जाएगा ना?
Exactly. So that would be on order of 1, which will constant. Let us see that solution. You're absolutely correct. So now let us see what we can do. From school level maths, arithmetic progression, we know that the sum of first n natural number is n into n minus 1 by 2. So what we can do is, let me just another file, fsum dot cpp. Just copy this code. And instead of doing this whole thing, what we can do is sum equals to
भाई n -1 की जगह n + 1 होगा.
yeah, I did that mistake. I saw that, like n plus 1 होगा. Okay, I guess. Okay,
हाँ 1 plus लास्ट फर्स्ट टर्म प्लस लास्ट टर्म होता है.
okay. Oh right, yeah, that's my mistake. Okay, just pardon. Okay, so the sum is n plus 1 divided by 2. So now how many operations we are performing? We are just ignoring these things. So this is an one line calculation, right? This is just an one operation. So our total number of operation is 1. Hence our order is also 1. So it is whether we are giving 4 crore, it does not matter. Whether we are giving the value of n is 4 crore, it will not matter. It will just give us the result in constant time. Let us see if it's giving the same result. So if I give 5, yeah, it is giving, the summation is 15. So we can see this is also working very efficient, like this is also working and much more efficient than this our earlier approach. Whether this may seem simple, well, why we are doing this thing at the very first place? Well, this may seem simple to you because you have learned arithmetic progression, but for a guy who have not yet learned arithmetic progression, this thing is like is a wonder to him. Like it's reducing from O of n to O of 1 just by using maths. So that way, using efficient algorithms, we can drastically reduce efficient algorithms and maths. We can drastically reduce the complexity or the time needed to solve the particular problem. This was a very easy examples, but while doing more complex problems like in competitive coding, you will see that using maths and its formulas really do reduce the time to solve a problem. So I hope it was understandable. So I will share this PDFs after refining its sum. So the complexity becomes O of 1. Let us take another example. So this was very easy, I understand, but let us take another example, slowly progress. So let us make a program to find, okay, there was any doubt in this thing, you can just directly put in the chat box. Yeah, definitely it's always preferable. Is O of 1 is always preferable? Yeah, it is always preferable because you see, like the most common complexities of the algorithm, those are like I'm showing the most common, like the O of 1 is the least time taking, then comes O of log n, then comes O of n, then comes O of n log n, then comes O of n to the power c can be any value 1 2 3 4, and then comes like O of n factorial. So we can see that O of 1, its constant time is always the least and most preferable like approach. So if any solution can be done in O of 1, that's which sometimes is impossible suppose sorting an array. So maybe O of 1 is not possible. So if a solution can be done in O of 1, it is always preferable. You can see this chart. So these are quite common.
साइज का मतलब साइज का इशू नहीं आएगा ना, मतलब
no, that you will see after, like when studying other algorithms which will be taught later, that size will depend on the algorithm. So when we are trying to get fast time, so our size we need to allocate more size, and when we are trying to use less size or space, the time will go more. So you will see these things in further times because it is a characteristic of an algorithm. So we can't discuss all algorithms. So okay, so let's just proceed to the next example. I hope it was clear up to this point. Okay, find if a number n is prime or not. How a class 8 guy would do that? This is why not class 8? Just we can say how would we do that? Like from 1 to n, we will see every number, not 1. From 2 to n minus 1, we will check every number whether it divides n. And if we see that no number divides n, so we can just tell, okay, so this number is not divisible by any number other than 1 and itself. So we can say that number is prime, right? So I'll not just write its code. I have saved those in examples, so I'll just show it because it will already have like reached up to 1.5 hours. So prime.cpp. So what I'll just quickly show what it's doing. So it is the driver code. So I have not taken input. I was just testing. Okay, just we have defined a function and giving it a integer to check if it's prime. And what this line is doing, can anyone say? Because Fahim taught it quite well in the last session. What this things means, what this things means. Can anyone say?
अगर ये वाला true होगा तो ये चलाना नहीं तो वो.
Yeah, exactly. So if this is like similar to writing if and else. So this things is just you don't have to write if else. So if this is true, then this will be executed. If this is false, then this will be executed. It was taught in the last session. So what we are doing in this function is we are taking the integer n, and we are doing the same thing which that guy would do. Like if we are taking an integer I and then assigning it a value 2, and we are taking it up to n. And if any number among it divides the n, so we are just returning false, that it is not prime, and there is no number that been false, so we are just returning true. So I guess there is an error. Let me just check it out. Also, it's perfectly working. So we are can anyone like we have already see how the complexity works. So can anyone say, I will just remove these lines. Can anyone say that what is the complexity of this program? How many operations are we performing in the very first place? What is the complexity of this program?
N times.
Yeah, it is n. So because the complexity is n, because the number of operations are like it is, the comparison is taking n times. These things are also getting executed n times. This comparison, this thing. So what we can say is the overall operation is near about 3n, 4n, whatever, and so it will be in order of n. So is there any way we can improve this algorithm? Like, is there any way we can say this thing faster? Like,
रूट कर दिया जाता है.
Yup, exactly. Can you say why so?
क्योंकि अगर मान लो कि उसका उस नंबर का स्क्वायर कर देता तो वो नंबर मिल जाएगा हमको एग्जैक्टली.
Which number?
जैसे अब मान लो भाई कि 13 है, तो रूट 13 को अगर 2 टाइम कर देंगे तो क्या मिल जाएगा हम लोग? रूट 13 ही मिल जाएगा, I guess. उसी से लिहाज से.
Yeah, it's quite correct, but it was not. I'm not sure. Like it was understandable. Yeah, it is quite near. Let me just show. Like, okay, let us just first see if we can do anything better. So what the class 8 guy is doing, that he is checking every number from 2 to n minus 1 to see if the number is prime. If any number in between divides that number, he is saying, okay, this number is not prime. So what we can do,
वाला मतलब 13 को डिवाइड करता 2 से, मतलब वो 6 तक चेक करता.
Worst case here it is n is prime. Best case is when n is divisible by 2. Yeah, exactly. Worst case is n is prime, so it will just check this algorithm's worst case is n, and best case is 2. Just in the first try it gets that it's false, and if it's prime, it have to check all the possibilities. So yeah, and the average case it's also like n by 2 or something. It's order of n, definitely. So okay, so yeah, what I was discussing that. Okay, so what we can do is what Deepak is trying to say, that we can, instead of seeing all numbers from 2 to n minus 1, we can just see numbers till 2 to root n, sqrt n. And I asked him why so. Can I explain why we are going only till square root of n? Okay, I'll explain. So if we don't find any factor of n within 2 to square root of n, we won't find any factor after square root of n. Why so? Because this is 1 and this, pardon, I am just writing using my mouse. So if there is, I assume there is root n. So if I assume that there is no factor till root n, so this number will be prime. But how can I say this? Because suppose there is a number root n plus 1, let me assume, and this is a factor of n. But this can be never factor of n, because if we do root n minus 1 into something, because if it's a factor, then it has to be multiplied with something, right? And if it's multiplied with something, that multiplication thing cannot be till root n, because we have already said, because until that point there is no factor. There has to be, the factor has to be right side of root n. So
root n minus 1 तो वो छोटा हो गया ना,
root n plus 1, right? I'm being obsessed with minus 1, sorry. So we have, as we have already said, that there will be no factor in this region. So the factor must lie after this root n. So if the factor is lying after root n, so let's assume that root n plus c. So this multiplication will always be greater than n plus something. So it will be always be greater than n. So it is not being the, it is not being the factor of n, right? So if there is no factor till root n, there can't be any factor after that. Because if there are any factor after that, then it has to be multiplied with any other factor, right? And that factor also have to lie after root n. And if we are multiplying those terms, that will be greater than n. So from this is a very common thing. So you can just understand intuitively that that any factor has to lie after before root n, and no factors can lie after root n. So what we can do, that we can reduce this counter, the loop counter, which we are taking till n. We can reduce it to root n, square root of n. Let me just find that, sum till n. Prime. So as you can see in this code, we have reduced the loop counter till square root of n. So what it will do, like in the earlier, it was this loop was being executed n times, and now it will be executed square root of n times. So earlier it was n to the power 1, and now it has become n to the power half, right? It may not seem that much big, but it will make a big difference in terms of big N. Suppose a number is there which is like in 10 to the power 10 to the power 10 order, like so. So suppose the number is a to the power n. So instead of counting till a to the power n, we can just count till a to the power 5, and that is a huge improvement, considering that in 1 second the operation performed is approximately 10 to the power 8. So in many contests in competitive programming, you will get time limit error because of this. So yeah, this is a quite nice thing to keep in mind. So we can reduce the complexity from n to square root of n to the power half. So I hope you are somewhat getting how we make our codes efficient. These are very basic examples. We cannot move to very complex examples because we have not done array or string yet. So the major use will come after that, like when we study sorting or searching. So from these basic examples, you can see how an inefficient code is being made efficient, and how we are just reducing the time complexity. We have a final example, the GCD of two numbers. Was this understandable till this point? Yeah, using math and human logic to help reduce complexity of numbers, right? Anyone any doubt? Okay, I hope not. So let us just move to the last example. I guess it is very tiring. It's been almost more than 1.5 hours. Okay, I'll just end after this if it has anything to say. If not, so let us find GCD of two numbers. So what is GCD? I guess most of us know that the greatest common divisor of two numbers. So if we have two numbers, that is A and B, we have to find largest C, which will divide both A and B. So how we do that? So from the very definition, we can make an algorithm to find a number, to find the largest number which will divide both A and B. So we have two numbers, and we have to find the largest number which will divide the both A and B. So what we can do, what any kid without the knowledge of math or anything, what he will do, from reading this line. So he will just say, okay, let me count from 1 and go, and let's count from 1 and go till A or B, whichever is minimum. And we will see that if a number is dividing both A and B, so we'll just store that number. Okay, this is dividing, and then we move on. Suppose 2 is dividing both A and B. Then we'll move to 3. If 3 is dividing, okay, 3 is a GCD. Then we'll 4. If 4 is not dividing, okay, let's go to 5. And this way we'll just go to minimum of A and B. And that way, whenever a number is coming to us that is dividing both A and B, we can just store that number. And at the final call, we'll just have the largest number, which is dividing both A and B. And thus we can say that that number is GCD of A and B. I'll again not write the code and bore you. Just let us go to the gcd.cpp. Okay, let us see what it is doing. It is taking two numbers as input. It's initializing I equals to 1 and another thing as answer. So yeah, so what is happening in this loop? So just the thing that this boy is doing. So we are just we have taken I equals to 1. So that will definitely divide the minimum of A and B. So our answer will be initially 1, and then I will be increased to 2, increased to 3, and the minimum, it will go till minimum of A and B. Why minimum of A and B? Because intuitively, if I surpass the A or B, so that definitely a value larger than A cannot divide A, right? So that's definitely we are going till the minimum of A and B. So what we are doing that if I divides both A and B, so this is called the modulus. If the modulus of A mod I is 0, also B mod I is 0. So the remainder is 0. So means that I is dividing both A and B. So then we can say, okay, answer equals to I. So just store this thing and increment the I, whether answer is I or whether this is true or not. So how many operations are there? There are 2 comparisons, 1 assignment, and one increment. So there are total 4 operations. So we can see that this code is in order of. Can you say what is the order of this code?
4n.
N is not in this code. So you have to tell in terms of A, B, and anything.
हाँ अच्छा अम्मा A अगर छोटा हुआ तो 4a.
Yeah, it's right. So like order of minimum of A and B. Yeah, it is totally correct. It will be order of minimum of A and B. So this code is in order of minimum of A and B. Can we reduce it somehow? So now we'll see some like actual
divide करेंगे B से.
A को B से divide करेंगे. Yeah,
उसके बाद से remainder मिलेगा तो.
Yeah, that's an Euclidean algorithm. So now we'll see some real algorithms. We're just like doing playing with stuff till now this point. So because this is algorithm analysis, right? You have to see an algorithm. So is there any better approach we can find GCD of A and B in less time than O of min of A and B? So now we have to search, like we cannot just invent algorithm, we can't invent algorithm. But anyway, we have to find that what algorithm is there to find GCD. And one such algorithm is Euclid's algorithm. How it works? Okay, so let us just, because how it works, it is pretty tough to like make you give you the derivation of how it works. But I'll just given this like just 1-2 line thing, and you can just, if you are interested, you can go home and like check why it works. So it works on the principle that GCD of A and B will always be equal to of. Okay, let's me just before I write a line, A equals to QB plus R. So there is A and B are any numbers. So just like this A or B, and we can write A equals to QB and QB plus R, just assuming that A is greater than B. So a number will be greater than the other. It is fine. So this Euclid's algorithm works on the principle that GCD of A and B equals to GCD of even not GCD. GCD of A and B equals to GCD of B and R. So you will ask how this works. So it comes in the domain of discrete structure, and we are not going to discuss those, but just to give you a hint that this is the basis of this algorithm, because GCD of A and B equals to GCD of B and R. So this we can define some way to find the GCD using this thing. So now we'll say how it will help. So we can see that R is we can say that R is one of the R will be R is A mod B, right? So one of the in the set R, there is the one value will be A mod B, right? Because it is the modulus, like the Q. If the Q's value is maximum, then the R value will be R will be equal to A mod B. So we can say that GCD of A B equals to GCD of B comma A percentage D, and this opens a lot nice way to find GCD for two numbers. So let us see how we are doing that. So let me just go to efficient GCD. Okay. So what we are trying to do is, okay, so we have A and B. So at first we are doing B and A percentage B, and we are repeating this process. Then again, what we will do equals to GCD of A percentage B, comma, it will be A percentage B. So it will be B percentage A percentage B. Is it understandable? Like, we will repeat this process until this term becomes 0, and this terms becomes the GCD, because we know the GCD of any terms and 0 and any term will be this term only. GCD of 5 and 0 is 5. GCD of, like, so that way this algorithm will work. We'll just repeat this process till this part, this B becomes 0. So what we are trying this, while this B is not becoming 0, we are storing this value of A mod B. This A mod B we are storing, and then in place of A we are writing B, and in place of B we are writing A mod B, right? The exact thing which we did in this step. Then we are repeating this step until the value at position B is becoming 0. Why? Because we have to find the GCD. That way, if the GCD equals to let us assume K comma 0. When after a lot of steps, when the GCD, it will be GCD of K of 0, we can instantaneously say, we do not have to do anything, that GCD of 0 and K will be K. So that way this algorithm works, and to calculate its complexity, it will be quite hard, like to go through all the derivations and to do. So I'll just say, like, its complexity is log of minimum of A and B. So you can see just like the okay, before that, let us see if this algorithm is even working. 12 and 4, it will come with 4. Let us take some examples. 11, 66. Will this thing work? 66. What is it? Yeah, this code is working. You can see that this thing is working. It would be more better. It have been more better if I had written this now, but the time is quite exhausting, so I'm just showing it. So yeah, the code is working, and this is the basis of the code, that if you want to explore more that why this is working, how this is working, why this, so you can just deep dive and search how Euclidean algorithm is work and see its proofs and derivations. But mostly you need to know the use more than the proofs. So yeah, that is still this. I guess I have exhausted my slides. Yeah, this is this Euclidean algorithm. It works in the complexity of log of minimum of A and B. So we can see we already reduced it from minimum of, if we assume that the minimum of A and B is, for example, n. So we have reduced the complexity from n to log n, and from there we can see there is a big gap, like the n and log n. There is a huge gap. See, the n is this and the log n is this. Sorry, not this. So this. So the log n is almost like, compared to this algorithms, it is almost like stick to base. So we have like reduced the time. So yeah, we could have like showed more algorithms, but because it is a characteristic, the complexity analysis is the characteristics of algorithms, so it is incomplete to like say these things without algorithms. But in further sessions, you will see that this is the very basic thing, and it will be widely used in the upcoming sessions, because in the searching every algorithm, there will be the complexity analysis, and it is as we have heard from our seniors, it is like quite asked in the interview and all, and also it is quite important. So do check this properly out. And okay, so my examples will end here. I don't think I have anything more to say. Simit, will you like have
Yeah,
like
yeah. Okay. Let me
So
present
just-
my screen and I'll tell you the solution. Okay, I hope it is visible. Right. So this was the question, right? I is starting from 0. It is going until n, and at each step we are okay. Sorry, I was disconnected.
Yeah,
Is it visible?
I'm audible now. Yeah,
Okay, okay, okay. So, so let's see the solution. So, let's see. Like, we have to go till n, right? So, initial value of I is 0. We perform some operation that takes a constant amount of time. Then, like, these are the values. Then we make I equals 2 into 0. Did I forget? Sorry. So it should be starting from 1. Make a correction. There is a correction. I'll correct it and share slides. Okay. So I is starting from 0, 1, and we are going until 1. And each time we are kind of like multiplying
Hi, your voice
I
is like
and assigning it by. Sorry. Clear? Am I not? Can you just
you're audible, I guess now. Your voice was breaking. Yeah.
okay. So for first time I is done. Then what we are doing, we perform some operation. Then we make I equals 2, like 2 into 1. Then we made. Then we performed operations again. Then we made I as 2 to the power 2, right? Then we made I as 2 to the power 3, and we are doing till some 2 to the power k such that 2 to the power k is less than n. Okay, am I disconnected again, or is it visible?
It is visible, I guess. Your voice was breaking.
Okay, okay, actually, it is. It might be some kind of. Okay. So we're going until 2 to is less than. That's what the condition is. I'm not able to write. Okay. So we made 2, then 2 square, then 2 cube, and we are going till 2 to the power k is less than n. Right. Once 2 to the power k then we'll multiply it will become 2 to the power k plus 1. Suppose this is greater than n and this is less than n. So here we have to stop. Right? Now we have performed k steps. Right? Each time we performed an O of 1 operation, and total number of steps is k. Right? We have performed k number of steps. Okay, so the complexity will be O of k. Right? Because we have iterated k times. Now 2 to the power k, right, is less than n. Okay, so from this we can write k is less than log of n. Okay, so the upper bound of k is log of n. Okay, so if n is some power of 2, then k would be equal to log of n. Right. So the complexity will be equal to O of log n. Okay. So I hope it is clear. So I had promised to show some examples regarding space-time trade-off, but it is, I guess, very
It's almost 2 hours.
yeah, it is almost 2 hours, but
We will get to see that
we can
in
end,
further.
yeah, I guess we can end it. You will come to see a lot of space-time trade-offs in the later session when we'll write, we'll come to more algorithms. So it's not a big deal. Okay.
Yep.
So,
Also, so should we end it here, I guess? Okay.
yeah, we can. Anyone has a doubt, you can ask right now.